So today's topic is like the coolest name of any math topic ever, seriously. We're gonna do, whoops, not that then. Power series. I mean, doesn't that just sound cool? You know, and you know, it's like, you gotta have your Power Rangers in the background and do your power series and just, yeah. This is why we study this, for what we're going to be doing next. Of all of the things that you do in calculus, and I was just having a discussion with one of the other instructors who understands how to, this stuff you carry on, of all of the things you ever do in your life in mathematics, if you continue going, outside of statistics, you will never use calculus again in all likelihood. Calculus is a tool for physics. You don't do anything in math with calculus. Calculus is really just algebra on steroids as you get higher up. But this kind of stuff is used in many, many situations outside of this class. So I mentioned last day, we're going to start a new concept today that it's the second half. It's something called functional analysis. And the idea with functional analysis is anything you can write algebraically, any function whatsoever, and again, it's got to be a function, but any function you could write whatsoever is equal to a power series. We're going to prove that over the next few days. Now that sounds kind of crazy, but what's a power series? It's a series, right? It goes to infinity, but it involves variables. So here's the formal definition. We're going to start like this. C is a constant. Most of the time, C is going to be 0. Most of the time. Sometimes C will be 1, but C can actually be any real number. Okay? And we'll talk about the rules and such. But we give sort of the general. This is the same AN we've been using all along. Now notice something is a little different here. I'm starting at 0, and here's the reason. If I expand this, let's just do the first few terms. So the first would be A0, oops, okay, times that quantity raised to the 0 with power. Oh, okay, so it's just A0 plus A1 x minus c plus A2 x minus c squared. So what do you notice? That this is a polynomial. And because we're starting at 0, the first term is therefore a constant, and then the second term is the x, the third term is the x squared, and so on. You're never going to multiply this out. There'd be no logic, because this is going to go forever. Now, if c happens to be 0, okay, that's fine. That doesn't make it easier or harder. It just basically, it's sort of like, where is your graph? So if I were to graph this using Desmos, it's where's my graph centered? So whatever c is. So we say this is expanded about x equals c. Okay? Now, you're either going to be handed a power series and asked to analyze it, or you're going to be given a function, this is a little bit later, and you're going to be asked to come up with the power series. Okay? So your choice in that case, when you're coming up with the power series, most of the time you're going to choose c equals 0 because it's convenient. And essentially every problem that exists that c isn't 0, c is going to be 1. And that's it. I've never run across any problem where it was different than those two. But when we're doing the analysis from this side, just saying, how do I manipulate these? We'll use all sorts of values of c, just so we can see the algebra involved. Now, this guy here, this is my power series. This isn't necessarily any specific function. Okay? We're going to prove later that every function has a very specific power series. But every power series does not necessarily translate into some function. So there's no function that I can tell you this equals, because it's just this polynomial. But we can use this to answer all sorts of questions. Now the main thing I'm concerned about is whether this converges or diverges. Because if this diverges, it's not very useful, is it? I can't really answer any questions. Well, here's the cool thing about power series. Every power series converges. Every power series converges. But it does not necessarily converge for all values of x. See, x is a variable. That's given, right? This is just the same ANs as before. That's a constant. But x is a variable. X can be anything. So every power series converges, but does it converge for all real numbers, or does it just converge over some interval? And that's what we need to determine where this converges. And that's the whole point of today's lecture, is determining where a power series converges in general. So let's start with something fairly simple. So let's start with, let's say we've got, how about 1 over 2 to the n, and we're going to do x minus 3 to the nth power, n equals 0 to infinity. Okay, so if I expanded this, this would be a polynomial, and I can see the coefficients are going to get really big in the denominator. But if x was a really large number, then I'd have a bigger exponential on top than on bottom, wouldn't I? If x is something really close to 3, then my numerator is going to be really small while my denominator is going to be really big. So right, x can right now be anything. So what we have to do is determine where will this converge, where will this not converge. Okay? So how do I do that? Ratio test. Okay? It will always be the ratio test. Partly because it's always going to be in the form of an exponential. Okay? See right there? So our ratio test says we're going to take the limit as n goes to infinity. Now, what is the n plus first term? That would be 1 over 2 to the n plus 1 times x minus 3 to the n plus 1 over 1 over 2 to the n x minus 3 to the n in absolute value. If I don't use the absolute value, then I will not get the right answer, well, ever. I will always get the wrong answer because I've completely changed the nature of the solution. No, there has to be an absolute value there, always. Because the x isn't bounded yet. We have to figure out what x's make this true. Now, I don't know what the value of this is, but in order for this to converge, tell me something about this limit. If this was going to converge, tell me about the limit. It has to be a number.
Less than 1.
Less than 1. Beautiful. That's exactly it. I don't know what x is. I don't even know what x can be. I just know that needs to be smaller than 1 if this is going to converge. Am I going to get some canceling here? Mm-hmm. Oh, yes. Probably. We're going to get a lot of canceling. Everything's an exponential. So what am I going to get here?
You're going to get
well, I'm going to get an x plus 3 on top. And won't I get a 2 on the bottom? Yeah. What do you think? So I'm going to get 1/2 of x minus 3. I don't need the 1/2 in the absolute value, but I still need that guy in the absolute value. Now, all my n's canceled, didn't they? Mm-hmm. Oh, so that's just 1/2 of x minus 3. Beautiful. Well, that made it easier. I'm starting with, this is really the simplest of all the examples. Now, going back to here, do you recognize this series? What if I rewrite this like this? If I wrote it x minus 3 over 2, all raised to the nth power, doesn't this look geometric? Remember, x can only be one number at a time. So for any value of x, I have a fraction raised to the nth power. So that's geometric, isn't it? Oh, okay, yeah, that's why the absolute value of r needs to be less than 1. Okay, beautiful. So we did everything right, but here's maybe the most important thing. I need this to be less than 1. So in order for this to be less than 1, that means that x minus 3 in absolute value must be less than 2. I would really like to remove the absolute value. Do you guys remember how to do that? So I'd say negative 2 is less than positive 2. And then finally, if I add 3 to every term, what will I have? 1 is smaller than x, and that is smaller than 5. If I drew this on a number line, sometimes that makes it easier to see. The absolute value of x minus 3 has got to be smaller than 2. So I can only go in each direction 2 units. Hence, 1 to 5. Now, Am I including the endpoints or not including the endpoints in this case? Well, if I include the endpoints, then that would be equal to 1. And will a geometric series converge if the r equals 1? Or negative 1? No, it's got to be a strict inequality. So, the answer to this question, the question is actually, where does this converge? That's really always the question. Because it's always going to converge. It just might not converge very big. So we say this converges over the interval 1 to 5. And it's an open interval. By the way, what would our favorite answer be, do you think, for any problem?
0.
Where would we like everything to converge? Yeah, all real numbers. We'd really like that problem. That doesn't happen very often. It can happen. It's probably not going to happen very often, though. We would really rather it converges for all real numbers because that means there's no restrictions. I can use anything. So if I wanted to use this to answer any question, I can only use x values that are between 1 and 5. Now think about this logically. If x is between 1 and 5, then this quotient is always between negative 1 and 1 then, isn't it? Which means I have an r that is small enough that it's acting like a convergent geometric series. Okay? So this is our first example. Now there's 2 things that I want you to take from this final piece. This is called the interval of convergence. I will converge in this interval. But the interval really depended a lot on the fact that I expanded about the number 3. If I had expanded about the number 7, then wouldn't we be going 2 units in each direction from 7? What if I had expanded around the number negative 5? Then I would have gone 2 units in each direction from negative 5. Does that make sense? Right? Whatever was here, then I just used that. So it's not the interval that's the more important part. It's how far did I go in each direction? And how far did I go in each direction?
3, 2.
2. So 2 is called the radius of convergence. And that's actually the more important thing. The radius of convergence is 2, so I went 2 units in each direction from the number that we were expanding about, which was the number 3. If I put any number, just call that c generically, then isn't this going to say x minus c? And you would have said, okay, take c and go plus or minus 2 units, and then you'd give me your interval. But your interval would completely depend on where c was on the number line, but you're still only going 2 units in each direction. So the radius of convergence is 2. That's the most important part. The fact that I'm expanding about 3, you can also say it's centered at 3. I'm just going to go, okay, 2 units in each direction from that number. Okay, piece of cake. So sometimes you're asked the question, what's the interval of convergence? Sometimes you're asked the question, what's the radius? Which one are you finding first?
Interval.
Radius.
Radius. Yeah, you have to take that and then answer the interval. So you'd rather be asked radius, by the way. Because the radius is just a number. The interval is I take that number and I add and subtract to both ends. If I was convergent over the entire number line, then what would my radius of convergence be? If I converge for all real numbers, what would your radius of convergence be, do you think? Infinity. Yeah, that's actually our favorite answer. That's not a hard answer. That makes life easier because that would mean I have no restrictions. Most of the time we have restrictions. All right?
So just to verify, with this kind of problem, when you do the limit, which is what gives you the radius, if you get infinity, that's your favorite.
Oh, no. Whatever you get, you're going to say, I want this to be less than 1, and then I'm going to proceed from there. Infinite would be, oh, I can use all real numbers. Okay? the infinity doesn't come from here. This is the first thing I did. Now I'm going to manipulate this algebraically. Well, let's do the next example. I think it'll be more clear. All right? I can do 0, right? 0 factorial. So it is not necessary for you to expand these, by the way. There will be times when we do, just so we can see what's going on. But right now, all I have to do is just go straight to the ratio test. So the limit as n goes to infinity of x to the n plus 1 over n plus 1 factorial. Could I just go like this? Would that be legal? Yeah, I'm being lazy there appropriately. All right, does anything cancel? Well, I'm guessing a lot of stuff cancels. So let's see, let's be careful here. This is n plus 1 times n factorial, and that's x times x to the n. So I can get that. I got a lot of canceling, don't I? But not everything cancels. So what's left?
X over n plus 1.
I'm going to write it like this. 1 over n plus 1, because the n plus 1 does not have to be an absolute value. N is approaching infinity. That's never going to be a negative quantity. But the x has to be an absolute value. Okay. What is this limit? 0. Huh. And what do I need the limit to be? Less than 1. So for what values of x will this be less than 1?
All real numbers?
Yeah, all real numbers. The limit is 0. It didn't matter what x was. The limit is 0. Ooh, by the way, do we like this one? Yeah, this is our favorite one. The limit is 0. That literally means no matter what x is, the terms are getting really small really fast. So this will be true for all real numbers. So my interval is what? Negative infinity to infinity. So therefore my radius is infinite. Do you see an infinity in the calculation? No. You're saying this is true for all real numbers. That's why it's negative infinity to infinity. In that case, we got something that was not always going to be less than 1. We had to figure out what values of x made that statement true. In this case, the nature of the problem makes this one true. So this was easier, wasn't it? We like that one. Every problem has a little bit different look to it. Before I move on, any question on this? Okay, we're going to be going through these, every version we can look at.
I'm just curious, if you can do the ratio, can you do the root test also?
Yes, you can, but you're going to find in general, because this is always going to be exponential in nature, you can always use the ratio test. In the first example, could I have used the root test in the first one? Mm-hmm. Absolutely. Could I have in this one? No, because of the factorials. So what you're going to find is, just out of convenience, you're probably always going to do the ratio test. Absolutely, you could have done the root test on the first one. But that's only because they were both exponential in nature, and that's not going to be as common. Okay? And by the way, that is the right question. But it's one or the other. There's no limit tests here. There's no integral tests. Those will come, but not yet. So, now let's do the most probably common form of a problem we're going to see. Let's say I have okay, this one's pretty generic. I am expanding about the number -4. So that means whatever my answer is, it's literally starting from -4 and then going in both directions, in a sense. Okay? I'm guaranteeing you this does converge somewhat. Now, we're going to look at extreme examples also. Every power series will converge somewhat. So when I start my ratio test, I'm going to have 1 over n plus 1, 3 to the n plus 1, x plus 4 to the n plus 1, over 1 over n 3 to the n x plus 4 to the n. I want to go over here just for a moment. If I didn't have the absolute value here, would I get the same interval? No, I'd get negative infinity to positive 5, which is kind of different than 1 to 5. Everybody understand that? Negative infinity to positive 5 is an infinitely large interval. This is a really small interval. Okay? If I don't have the absolute value, it's impossible to get the same answer. Okay? So I want to make sure I don't forget that. Now, does this cancel nicely? Usually things cancel very nicely. Okay? Not everything, but most of this is going to cancel beautifully. Now, I'm only going to put the x's in the absolute value. So here's what I do know. Does everyone agree that that's part of my answer? That makes it a little bit easier. But what's left? Get rid of some 3's. I got some n's, some n plus 1's. If you want, flip that up and put it on top. That might make it easier. So what's this term going to be?
N over 3n plus 1.
That is correct. Did everyone see that? You know, manipulate it, rewrite it, do whatever you need to. Now, when I take that limit, that's not going to be 0. The x plus 4 literally isn't even part of the limit. The limit only involves the n. So whatever I get, it's going to be multiplied by x plus 4. Okay? So what is the limit of this part? 1/3? Everybody agree? Same degree. So this is equal to 1/3 the absolute value of x plus 4. It is equal to this. Okay, so I'm basically done with anything calculaic here. Oops. Well, this is, oops. Let's reflow that one. All right, this is less than 1. The algebra to proceed shouldn't be too taxing, so doesn't that mean that x plus 4 is less than what? 3. Can you tell me what the radius of convergence is? It's 3. That's the easy one. The radius of convergence is not 1. Right? I have to get rid of that coefficient. Now I can tell you, oh, okay, I'm going to go 3 units in each direction from the number -4. So can you tell me the interval now? I'll write it up here. I'm going to be lazy.
-7.
-4 plus or minus 3 would be what, Chase? -7 to negative. Oh, good. -1. Now, I'm almost done. In the first example, I asked the question, can I converge at either one of these endpoints? And the answer was no, because then that would give me, basically it would give me an R of 1 or -1. And that first problem was actually a geometric series. On a geometric series, you cannot converge at the endpoints, because that means you're going to have an R of 1 or -1. Is this a geometric series? That problem right there, is that a geometric series? No, because the n on the bottom. Now, it thinks it's geometric. It's asymptotic to a geometric series, but it is not a geometric series. So why am I pointing that out? Because I may get convergence at the endpoints. A geometric series can't, because if I put a 5 in here, now I have 2 to the n over 2 to the n, which is 1, and you just added up the number 1 infinitely many times. If I put 1 in here, now I have -2 to the n over 2 to the n, which is -1 to the n, which just goes back and forth between 1 and -1 forever and ever and ever, and that diverges also. In a geometric series, the R cannot be 1 or -1. We already know that. R has to be smaller than 1 in absolute value. This is geometric. This is more of an observation. This is not geometric. So now I'm adding one thing to the problem that you have to do. I know with absolute certainty that I am converging in this interval. I know that. But there's a possibility that I may converge at one or both of the endpoints. So how do I test that? You plug them in and look at that series, and now it'll feel like we're going back in time. So It does not matter which one you do first, but if I put a -7 in here, won't I have -3 to a power? And that alternates.
Yes.
If I put in -1, I'll have +3 to a power. That does not alternate. My suggestion is, if you want to save a little time in the long run, put in the number that doesn't make it alternate. And then determine if that converges or diverges. And the reason is, if that one converges, then the alternating one automatically converges, absolutely. If the non-alternating doesn't converge, now I got to test the other one because I might get conditional convergence. But I could be saving a step depending on which one I do first. I don't always have to check them both, in other words. So let's start with the -1. Now, this is the only part of the problem where there's really a little bit of work involved. Okay, so we will start with x equals -1. If I replace x with -1, what does my series become? Actually, you know, I'm sorry, this should be a 1, not a 0. My bad. That should be a 1. What does my series become if I replace x with 1? I'm sorry, with -1. It'll just be 1 over n, won't it? Because I'll have 3 to the n on top, 3 to the n on bottom. They will cancel very nicely. Oh, okay. Do you need to do any work here? Doesn't this diverge? It's the harmonic series. Okay, so I didn't converge there. All right, that was easy enough. How about if x is -7? Then that means I'm going to have a -3 to the n on top and a +3 to the n on bottom. Does anything cancel there? I'm going to have -3 to the n over 3 to the n. Well, isn't that the same as saying -3 over 3 all raised to the n? Which is what? -1 to the n. Ooh. Does this feel like something we maybe have done, I don't know, recently? Like a significant portion of Monday's class? This is an alternating series. I know the non-alternating diverges. But this one I'm going to perform the nth term test on, and it's going to pass. In other words, the nth term test on this, so this one's going to converge conditionally. I'm going to save the trouble because this is one we've already done a couple times. I'm sorry, converges conditionally. Is that important? Yeah. Because now I have a different final answer. That was only the final answer, it wasn't the final answer. So what is my answer actually going to be then?
So -7 is less than or equal to, oh, there.
Yeah, it's easier to just write in that form. I guaranteed you we were going to converge over the open interval. I'm guaranteeing you that. Then I'm asking the question, could I also converge at the endpoints? Could I also converge at the endpoints? Now there's, the example I did a moment ago with the factorial, we got a limit of 0. That's the easiest problem there is because it converges for all real numbers. I threw that one out there to show you it can come up, but that's not the regular. This is probably the most common type of problem. So when you do the problem, and you figure out you converge over some open interval, not the whole number line, now you have to test both endpoints. You're either going to converge at both endpoints, at neither endpoint, or, like in this example, one of the endpoints. That's probably the most common one. If I'm only going to converge at one of the endpoints, and by the way, every single problem will be an alternating series, won't it? Everybody understands that? For every value of x that is greater than -4, this is non-alternating. For every value of x that's less than -4, this is alternating. Every problem you look at from now on is going to be an alternating series in some form. If I only converge at one endpoint, it's got to be the alternating one, because I can get conditional convergence. So if I fail at the non-alternating, I can still pass the alternating. What if I converge at the non-alternating? Then I automatically converge at the alternating. That's absolute convergence. Can I fail at both?
Yes.
Yes, you can. So we're going to look at every single version. I don't want you to try to guess an answer. Sometimes we try to be clever and we try to see the answer down the road. but it may not work. The process is not complicated. And it's going to be the same process no matter how different the problems look. The process I want you to get really comfortable and really fast at and good at, because it's the thing we're going to be doing the most common. So this is probably the most universally common form of the problem. Let's try another one. Let's say we've got x minus 1. Now, could I start this at 0? Would it cause any problems if I started this at 0? The answer is no, but the first term of a power series, or any series, cannot be 0. If I started this at 0, wouldn't my first term be 0? So in other words, I don't have a constant term in this power series, so we just started at 1. That's not, you're not violating some universal law, but the thing is, we define a power series as being the non-negative things. Now, down the road, it's always possible that you could have a 0 term down the road, but you just don't, your first term can't be 0, your first term can't be undefined, right? They all have to be nice numbers. So here's my power series, okay? You're seeing that n squared and going, isn't this going to diverge? Not necessarily. So when I do my limit, I'm going to have n plus 1 squared, x minus 1 to the n plus 1, all over n squared, x minus 1 to the nth. Okay? And let's see, what does this give us then? I believe I'm going to get n plus 1 squared over n squared times the absolute value of x minus 1. Well, what's the limit of this? That's just 1. I don't want you to do this, but this is actually correct. I could write it like this. Oops. I've seen textbooks do this to try to make it easier on you. I don't think this makes it easier on you. This is not subject to the limit. It's not changing. You can think of this literally as a constant. So it's completely outside the limit. So the limit only involves the n terms. I don't want you to rewrite it factored out. That's overkill. Just recognize, oh, okay. So what is my answer? It's just x minus 1 in absolute value. Oh, well, that's easy enough. And I don't even have a coefficient. Wow, this is pretty friendly. And I need this to be
Less than 1.
less than 1, which will, oh, by the way, what's my radius of convergence here?
1.
1. So I'm going to go 1 unit in each direction from the number 1. By the way, it is absolutely correct to do this, then add 1 to every term, and do this. I'm far lazier than that. I'm centered about the number 1, and I want you to go 1 unit in each direction. Can't you just tell me 0 to 2? Do you really have to do all the algebra, or can you say, yeah, it's the number 1 plus or minus 1? That's where 0 to 2. So with absolute certainty, again, I keep using absolute, where will this converge? Before I test, I know it will converge where?
Between 0 and 2?
The open interval from 0 to 2. So far, so good? So now let's test the endpoints. I'll do it over here. So let's start with x equals 2. If x equals 2, then 2 minus 1 to the nth power is just what? If I replace x with the number 2, that's just 1 to the nth, which is 1. Oh, okay. Does this converge or diverge? Is this a p-series technically? Yeah, it doesn't look like a p-series, but it is. Don't rewrite this, please. And that p is small. Remember, p has to be greater than 1. That's -2. That's definitely less. Does this diverge? Yeah, these terms are getting huge. So this diverges. Agreed? I mean, it's exponential in nature. Now, why does it diverge? Well, it's a divergent p-series, or really simple, do my terms approach 0? No. Do they get smaller? No. So I have drastically failed the nth term test. Do I need to check the alternating? No, I already failed the nth term test. So therefore, I'm not going to converge at either endpoint. These terms are getting bigger. So if I do x equals 0, that means it'll now be -1 to the n. If this one diverges to infinity, this is way worse. This is the alternating divergence without limit. This one is just awful. But these both diverge. So therefore, this is the answer to the question. And the radius of convergence is
1.
It is what? Inside voices, right? Inside voices. Where's my? Oh, I left it way over there. So this is the part that gets people the most trouble when I test the endpoints. But I want you to realize when you're testing the endpoints, you're going to be testing probably a very, very simple series, and it's going to look like the things that you've been working on for the last few weeks. Now, this one's kind of odd because you go, wait a minute, I don't have a denominator, right? So these are getting really big, really fast, and right, they're not approaching 0. It's going to fail the nth term test. That's actually a lot easier if I look at it that way. All right, so let's try another one. Let's do n equals 0 to infinity of, how about 4 to the n over n plus 1 squared times, well, let's just make this x to the n. Let's just have fun. Times x to the n. We'll leave it like that. If I said, what am I expanding about in this power series? What would you tell me?
X to 0.
0. Because it's technically x minus 0. And expanding about 0, we're going to find is the most common. It is not always. No, not even close. But the most common problem, we're going to expand about 0. Well, how would I know? Because you don't see another number there. You see x. Oh, it's x minus 0. See, this one was expanded about 1. That one's expanded about 0. That doesn't change any aspect of how I do the problem. Nothing. It doesn't make any part of the problem easier, by the way. It's just the most common form. All right, so let's do this. So when we set up, by the way, can I start at 0? Yeah, that means there's going to be a constant term. When n equals 0, I have an x to the 0 power. That means I have a constant term, and then the next term will be x, and then x squared, and so on. Okay, that's what we usually see. So I have the limit. All right, so we have 4 to the n plus 1 over what? N plus 2, yeah. X to the n plus 1. 4 to the n over n plus 1 squared, x to the n. All of the exponential terms should cancel very nicely. I'm still going to have some polynomial-ish things left, but I don't worry about that part. And I'm going to show you some commonalities, some things you're going to see pretty much every time. All right. I'd rather not rewrite this, but I also don't want to make any mistakes. So what I'm probably going to do is something like this. I think that's pretty much all I got to do. And then that would be x times x to the n. So boom, boom, boom. boom, boom. So what am I left with? Okay, I know this part. We all agree? Can I have an absolute value of x there? It's the stuff in front that I gotta make sure I get right. I have a 4. What about this guy? Can I move that to the top? So I'm gonna have a 4 n plus 1 squared over n plus 2 squared. Does that look about right? Stare at that, make sure you agree. If I make an error, that kind of error I might make is have the 4 in the wrong place. I might have the 4 on the bottom inadvertently. Okay, that would change my answer quite a bit. So does that look okay? What does this equal? Same degree?
4.
4 absolute value of x? And I need that to be less than 1. Therefore, the absolute value of x needs to be less than 1/4. So far, so good. My interval of convergence. My radius is 1/4. That means it's a really, really small interval. I'm only going from -1/4 to +1/4. Another way of thinking about this, all real numbers that are bigger than 1/4 or smaller than -1/4, this is going to diverge. Crazy, isn't it? But, excuse me, that's what we're saying here. So, I'm going to converge in this interval. And let's see. I need to test endpoints now. Now I said, it doesn't matter which one you test first. But what I do is I always take the one that won't make it alternate. So in this case, the positive one. I'm going to start with that one.
So what does it converging between -1/4 and 1/4 mean?
Because when I do the ratio test and I get, this is the limit, but it's only going to converge if this is less than 1. And this will only be less than 1 if x is between here and here. For every other, let's just make it really simple. Just pick a x, 5. Okay, x is 5. You now have 4 to the n times 5 to the n on top. It doesn't really matter what the bottom is. That's ballooning out of control really fast, isn't it? But if x was, let's say, 1/10. Oh, now I have 4 to the n over 10 to the n. That's really small. That's going to converge really quickly. As long as x is really, really small, this will be a r that is smaller than 1 in absolute value. That's kind of what that says. Okay? Now, I need to test the endpoints. Which one should I check first? I said it doesn't matter, but I have a plan. The negative or the positive, do you think? Let's go with the positive one. So if x is +1/4, then what does this become? It's the sum of, if x is 1/4, then won't these just cancel? Did everybody see that? I don't have to even write it out. This is 1/4 to the n, that's 4 to the n, they cancel. And all I have is converge or diverge? Yeah, in fact, I can do a direct comparison with 1 over n squared. This is smaller than 1 over n squared. I can do a limit comparison with 1 over n squared. This is going to converge. Okay, the non-alternating series just converged. Do I need to test the negative?
No.
No. That's why we did the positive first. Because this converged, the negative is going to converge. Absolutely. Now, you still want to say that, so you can just write it like this. I'm explaining why this process just became easier. If x is -1/4, then the 4 to the n's cancel, but I would have a -1 to the n on top. And this converges, converges absolutely. We did one a little while ago where we got conditional convergence on the alternating, but because that converges, I don't have to do anything, this converges absolutely. So does that change my final answer in terms of the interval of convergence? Yeah, what does it make it?
Less than
Brackets.
or brackets.
Well, in an interval sense, probably it's easier to write it as an interval. Yeah. Writing it as an inequality is not incorrect. It's less useful. And writing it as an interval makes it easier. So it's going to now converge over that closed interval. This is not a geometric series. This term on the bottom makes it not a geometric series. That's why I may get convergence at the endpoints. So just hypothetically, what if? What if I remove that from the problem? You're going to do the same problem in the same way, and you're still going to get that statement right there, and you're going to get that statement right there, and you're going to get that statement right there. But is that now a geometric series? Yeah. In fact, if it makes it easier, isn't this 4x to the nth power?
Yeah.
And that means my r is 4x. So the only thing that has to be true is that it has to be less than 1 in absolute value, which is the same as saying that's less than 1/4 in absolute value. Same conclusion. But do I have to test the endpoints on this one? No, because it is geometric, I don't need to test the endpoints. It's going to fail at both of them automatically. You don't have a lot of geometric series in this realm, but it can come up. So if you recognize you have a geometric series, it automatically makes the problem easier. Because it is a geometric series, and all I have to do is have an r that's smaller than 1 in absolute value, and you never have to check the endpoints. But most of the time, that is not the case. Okay? Everybody okay with that? Most of the time, it's not going to be that nice. Okay. Let's do more. No, I'll just do to the end. I don't want to make it too complicated yet. That comes soon enough. All right, start the process for me. Factorials we know are going to be a little bit trickier, so go slow. So what does the n plus first term look like?
2n plus 1, or 2n plus 2.
It's technically this. If I put the factorial after the parenthesis, that's a very different statement. Okay. So as long as I know that's what it is, can I go directly to 2n plus 2 quantity?
Yes.
Yeah, I mean, if you can, just it's more efficient. But if you don't have a 2n plus 2, it's going to change everything. Okay. The common mistake would be to write what, do you think? 2n plus 1, because I'm thinking, okay, just add 1. But I'm adding 1 to the n, and then distributing the 2. Okay, on the bottom?
n plus 1. Factorial.
Quantity factorial. Quantity squared, oh my goodness. And then x minus 2 to the n plus 1. Let me get rid of this part. That's the numerator. And now 2n factorial, n factorial squared, x minus 2 to the n. Boy, okay. I don't have to do anything to the denominator. But I am going to need to expand the numerator, aren't I? I need to expand enough terms on the numerator that I can get cancellation. Okay? So maybe you rewrite it. I think it might be hard to write over this. It might make it a little bit too unreadable. So when I expand my numerator, what will this become?
2n plus 2 times 2n plus 1 factorial. Or times 2n factorial.
Not yet.
No?
I'm not done expanding the top yet, am I? Anything short of that, I won't get any cancellation. Yeah, I've got to expand until I get something that cancels on the bottom. Everybody got that? If I said, again, I want you to do, without a calculator, I'd like everybody here to do this problem, without a calculator. Well, wouldn't you all make the top be 10 times 9 times 8 factorial? And then you cancel the 8 factorials? I need to go 2 terms, because 2n plus 2 is 2 more than 2n. I need to go 2 terms in order to get canceling. But if I don't do that, those are the kind of errors that we may make, and it will, it'll change the answer quite a bit. Now, how about the bottom? N plus 1 factorial quantity squared. Wait. N plus 1 factorial is n plus 1 times n factorial, is it not?
And n plus 1 squared.
But I gotta square that, which means I gotta square that. Oh, so could I just write that as n plus 1 squared times n factorial squared?
Maybe we can cancel it.
I would strongly recommend you do scratch work off to the side. I think if you're, again, I'm a big fan of expanding right there because I'm really lazy and I hate rewriting. But I think there's too much information here for you to try to expand and rewrite and cancel. Pretty soon it's completely unreadable and we might not get the right thing. Now, that's my numerator. Can I just flip this over and write it next to it?
Yeah.
Save myself some time? Sure. So what's going to go on top here? The n factorial squared, and what's going to go on the bottom? The 2n factorial. Now, what about this? Well, that's the easiest part.
There's x minus 2 absolute value.
X minus 2 in absolute value to the first power. Can I evaluate this limit right now? No, it's still an indeterminate form. I got infinities all over the place. But can I reduce it? The problem is we cannot take limits when there are factorials involved. It's too crazy. But if I did this right, all my factorials should cancel. So let's see. Boom, 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 boom. And all I have left is a rational function. I can live with that. Rational functions, why? Because they're the easiest limits we know of. In Calc 1, that was literally third day of class, you did limits to infinity of rational functions, and you go, give me these all semester. There's no question on planet Earth that is difficult when it's a limit to infinity of a rational function. Just looking at degrees, right? And the best part about this is, let me rewrite this. By the way, can I factor a 2 out and cancel? Can I do that? Do I need to?
No.
It would not be incorrect, but do I need to?
No.
Nah. I'm impressed when people do that and they say, oh, I can get more canceling, but you're removing a degree from top and bottom, so you're not changing the answer no matter what you do. If you want to factor the numerator and cancel, that's fine. If you don't want to, that's fine also. Can I evaluate this limit now? Yes, that was our goal. If I can't evaluate this limit, then we're in trouble. Now, if I did this right, and you guys have noticed this, we proved this in class a couple weeks ago. If you do a ratio test on a P series, you will always get 1. Always. Because you're replacing n's with n plus 1s, but you're not affecting degree. So that's why you can't use the ratio test on a P series. But this is not a P series because of this additional term. So when I do the ratio test, these are always going to be same degree. Does everybody understand that? These are always going to be same degree because all I did was change x or n to n plus 1. I didn't mess with the degrees. So when I do the quotient of the n plus first term over the nth term, the degrees have to stay the same. So what is this limit here?
4.
4. So this is 4 times x minus 2. Oh, isn't that nice? And you thought it was going to be horrible. Well, a little bit.
Okay, so the reason that it works is because if you decided to multiply out the top, you would get like a square.
You'd get a 4n
get a
squared
4n
on top
squared.
and you get an n squared on the bottom. It is absolutely correct to factor and cancel here. I'm just saying, isn't going to change anything.
Yeah.
And by the way, it might make it easier to see the answer right in front of you. But as long as you say, oh, they're the same degree, I'm looking at lead coefficients only.
Yes.
Right? But don't lose the fact that it is a 2 times 2, right? So now I want this to be less than 1. So the absolute value of x minus 2 is less than 1/4. Therefore, my radius of convergence is 1? 1/4. Wow, that's a pretty small window. We did one like that already. I'm only going to move 1/4 from the number 2. So what does that give me? Think of 8/4.
9/4, 3.
So what, 7/4 to 9/4? Yikes. Yikes. Now, how about the endpoints? Can I converge at the endpoints? Well, let's see. Which one should I do first?
9/4.
We should do 9/4. So if I do the 9/4, which is 0 to infinity of 2n factorial over n factorial squared, and then I would have 1/4 to the n. So could I just write like that? Would that work?
Yeah.
And I would use a ratio test on this. And what would I find? That when I do the ratio test on this, I already know what the answer is going to be because we already did it. It's going to get all the way down to here, and you're going to get that this is less than 1. Or is it? No, when I do the ratio test on this, I'm going to get that it's equal to 1, aren't I?
Mm.
How do I know that? Because if I do the ratio test, isn't all the other stuff still going to be there? The only thing I changed was the x. So I'm saving you some time. Don't do the ratio test again. If this was on the quiz you just turned in, ratio and root test, this problem from the beginning, you would do the entire ratio and root test, and you know what you would get at the very end of the problem? You would get exactly this statement here with x replaced with 9/4. Which means what? That this quantity would exactly equal 1.
Which is.
Which is a problem. I don't want it to equal 1. I need it to be less than 1. So therefore, am I going to converge at the endpoints?
No.
No. So I'm saving you some time. Because the original test would have only been a ratio test. That does make it easier. Now, go backwards to what we did last day with alternating series. I said if you're doing an alternating series and now you're checking the non-alternating series, but you're using a ratio test, if it fails, it's automatically going to diverge in every conceivable case because your terms weren't getting smaller and they weren't approaching 0. Okay? You with me on that one? So this one is an interesting one. This was the ugliest one. Factorials present different problems to us. They present different issues altogether. Now, let's look at another one. I want to start looking at ones that are a little bit off center. Just a little bit. All right, let's do, how about n equal 1 to infinity. Let's do 1 over n x minus, well, let's say x plus 2, we haven't used x plus 2, and I'm going to do that to the 2n. Anything weird? Anything odd about this question? I don't think the 1 over n, we've done a couple like that so far. That's not the biggie. Anybody see anything odd? Nobody sees anything different about this one? It's not to the n, it's to the 2n. So does that change the way I attack this? No, we're still going to replace n with n plus 1. So when we do our limit, this can come up. And we will see versions of this. So I will get 1 over n plus 1, x plus 2 to what power?
2n plus 2.
2n plus 2. Good. Yeah.
I thought we were supposed to start at n equals 0 for these kind of things. Do we
Well-
always start at n equals 1?
No.
Or, never mind.
No, because I can't start at 0.
Right, because you can't divide by 0.
In general, a power series is going to start at 0 because it's a polynomial. And I'm going to have constant term plus everything else. But because of the definition I just gave you, I can't start at 0 because then I'd be undefined. So here's a power series that just doesn't have a constant term, in other words. What if my denominator was n plus 1? Could I start that one at 0? Yeah. What if my denominator was n minus 1? Then I'd have to start that one at 2, wouldn't I? Because again, I can't be undefined at any point of the problem. Okay, so I got this over this. Do I get any canceling? Well, let's do that part first. That's going to be n over n plus 1. And what about the x's? It's going to be x plus 2 squared. Do I need to write the absolute value in that case? It's not wrong, but do I need it in that case? It's being squared, so it's already non-negative. Oh, okay. And what does this equal? It's x plus 2 squared. Oh. And I need that to be less than 1. That squared presents kind of a quandary, doesn't it? Well, the quantity on the left is never negative, is it? Do you agree? But if I choose a large negative value for x, then the quantity on the left is going to be very large. So doesn't that still have to be true? Just think of the algebra, don't think complicated. I'm squaring something and that square has to be smaller than 1. Oh, then the number I'm squaring has to be smaller than 1. And so therefore, I'm going to go from -2, 1 unit, in each direction. And when I do that, what will my interval be? From the number -2. It'll be -3 to -1. Now, this one is trickier. It's trickier. I want to test my endpoints. This is not a geometric series. That 1 over n means it's not geometric.
Yeah, -1.
But that raising it to the 2n kind of makes it a little wonky, doesn't it? Am I going to get the same thing regardless of which endpoint I use? Stare at that for a minute. If I replace x with -1, then it will be +1 to the 2n, which is just 1. If I replace x with -3, then it's -1 to the 2n. Now that one we haven't seen a lot. True or false? Rules of exponents.
Yes.
Oh, I'm 1 at both ends, aren't I? Therefore, both -3 and -1 produce this series. And we know this series diverges. Therefore, that will be my final answer. I'm not going to get convergence at one of the endpoints. Okay, so throwing this in there just made it a little bit trickier, but it really didn't make it a harder problem. I just had to be a little more alert. I was never going to get negatives. Okay, there is no value in this series that will ever produce a negative number regardless of what x is. Now, the range of values of x, very narrow. And we're going to find that is the case often. Okay, so here's big picture where we're going. We are going to show over the next several days that if you give me a function, and we're going to concentrate on the really important ones, things like e to the x, sine x, cos x. If you give me a function, we're going to be able to show that it equals a power series, which is very powerful. And then using the power series, I don't necessarily need all the terms. Maybe I only need the first few terms. I can give really good estimations of the function by using the series. So why would I do that? Because sometimes the function itself might be too hard to deal with, but doing the series might be really, really simple, especially that I have technology. But it only helps if I know where that series converges, because not everything converges for all real numbers. Some series only converge for a very, very short range. Natural log is one we're going to show the series. It's a very powerful one. It's very important, but its interval of convergence is microscopic. So how useful it is tricky because it doesn't converge over a large range of numbers. But things like e to the x we're going to find converges for all real numbers. That's a very friendly one. Okay? Questions so far? All right, I'm going to give you a little bit of a glimpse into the future, and the only reason I'm going to do this is we have an exam on Wednesday next week. Monday we're doing new material, and it's pretty powerful stuff, and we're going to be doing a lot of stuff, but we're also going to be reviewing. So what I'm going to do is I'm going to give you a little piece of the stuff we're doing next day. We're still going to do it, but I'm going to give you a little piece now so I don't have to spend quite as many minutes on it because I don't want to compromise the review time. Because the stuff we're doing is actually quite huge. Okay, does that make sense? So I'm going to show you something that you already know a version of it, but in a different way. Okay, we know what is this? This is this is a geometric series. This will converge if and only if
R is less than 1.
the absolute value of R is less than 1.
Right.
We all agree with that. What will it converge to? Well, isn't it first term over 1 minus R? Well, what's first term?
1.
Oh, we like this one. I have to throw that disclaimer in there. That's a pretty small range of values, wouldn't you say? All real numbers? No, just those between -1 and 1. We know this is the definition of a geometric series. Now, I left out the A1, because if I put an A1 there, can't they just factor it out of the problem anyway? And then you're just multiplying. So don't even worry about the first number. If I write it in this form, we know this. So, throw a what if at you? Okay, it's a simple quotient. I'd like you to write it as a power series. How could I write that as a power series? Any ideas? I want you to write this as a power series.
X to the n.
How about x to the n? And just write the same thing with an x instead of an r? Oh, so here's the cool, I don't want to call it a trick, because it's a very important and valid technique. If I give you a rational function in general, this is pretty simple rational function, but if I give you a rational function in general, you can always write it as a power series without doing any extra work. That's what I'm going to show you next, because today's all about power series. This is just a continuation. Really? That's it? That's all I would have to do? Yeah. The key is, this is absolute. I don't have to prove this. We've already done this. There's got to be a disclaimer here.
X, absolute value of x
X
plus 1.
is less than,
If x were a large number, then wouldn't this be a very small negative fraction? But if x were a large number, wouldn't this balloon off to infinity really fast? And I don't think infinity is equal to a small negative number very often. Yeah, you still got to have that there. All right, so what if I asked a question like this? Could you write that as a power series? How the heck would I do that?
X to
I
the
thought I
power
wrote it
plus
like
one.
this. Keep going. Can I keep going?
Yes. X to the n plus 1.
X to the n plus 1? N can't leave the summation. N is the index. It's stuck, it's imprisoned into the summation. But if I had a coefficient here, couldn't I just pull it in and out? So think of X as literally as a coefficient. Cool, huh? Oh, by the way, should I also say that as long as that's true? Yeah. I just took a really simple rational function. Now, here's one of the reasons this is important to us. Think of derivatives and integrals. I don't think any of us would have issue differentiating or integrating something like this. That's not really the thing. But as I add to the level of complication of what I'm about to do here, then the level of complication of integrals and derivatives, you can see, can grow pretty quickly. But if I could tell you a power series that it was equal to, one of the reasons we really love power series is a power series technically is a polynomial. And aren't polynomials about the friendliest things to integrate and differentiate? So if I have a power series, could you, and we're going to do this next day, this is not part of today's class, could you take the derivative of this? Yeah, you could. It's actually quite simple. If we expand the first few terms, you could tell me what the derivative looks like. Could you tell me the integral of this? Yes, you could. It's actually not very difficult. That's stuff we're going to be doing in the future. Differentiating and integrating power series, because again, we're only integrating and differentiating a polynomial. All right? So let's keep going. I can't do anything unless it looks like that.